So thank you and welcome everyone to today's weather briefing. My name is Liliane Hofer, as Marco already mentioned, and I'm working for the Austrian Weather Service. I'm not situated at the headquarters in Vienna, but I'm sitting at the regional office here in Salzburg in the middle of Austria. And you can see this map here, and I would like you to show me where you are sitting at the moment, so that we get a nice overview. And can you start? Okay, yes, it works. Perfect. When I'm looking out of the window, I see partly sunny, partly cloudy conditions. So if you like to, you can also show me if you see more sun or more clouds. So if you see more sun, you can draw a plus sign. And if you see more clouds, you can draw a minus sign if you like to. So we could have a little overview over your observations or your weather observations. Okay. So Edwin in Dubai, hello. So I see some minus signs, mainly minus signs. Nobody sees the sun at the moment, as it looks like. So thank you for taking part in today's weather briefing. And let's continue to the next slide. So this weather briefing has the subtitle, The End of Summer, because that is what happened, at least in Austria, over the last few days. And so I would like to start with the weekend. I was on shift on the weekend, so I had to follow the weather real closely. And you can see now the highest temperatures on Saturday, and really hot conditions here over the south of Europe, cold in the northern parts, and here in Austria, in Germany, Czech Republic, Poland, you can see summer conditions. As you know, a summer day is defined if the temperature exceeds 25 degrees, and that's what happened all over Central Europe here. So a nice summerly day on Saturday. And now let's jump to the highest temperatures yesterday. And you can see, oh my God, what happened here? We have really temperatures under 20 degrees in most parts of Germany, Austria, Czech Republic, Poland. So yeah, we can really say the autumn is here for these parts of Europe. And when I started this weather briefing, I took a look all the satellite images from Saturday, because that's the day I wanted to start with. And so I want to start this weather briefing with a quick side note, because this natural color RGB attracted my attention. So I think the natural color RGB is always a nice thing to start presentation with, because it looks like you would expect things to look like. The ocean is blue, the land is green, the clouds are white or cyan colored. And so I always think this is a nice image to start with. But on this image, something is missing. And I would like to show you what I mean with the webcam image. The webcam is situated somewhere here in the mountain area of Salzburg, and it looks like this. So as you can see on the natural color image, some small heat clouds have appeared on this Saturday afternoon, but the sky is mainly overcast with high, thin cirrus clouds. And if you go back to the natural color RGB, you can't really see the cirrus clouds here. You can see the small heat clouds, but no cirrus clouds. And that is something the natural color RGB cannot achieve, to really highlight these cirrus clouds, because they are optically too thin. And if we compare this natural color RGB with the dust RGB from Saturday, you can really see the cirrus clouds are really highlighted here in these blackish colors with the help of the dust RGB, and you can't really see them on the natural color RGB. Dust RGB uses brightness temperature differences of the infrared channels, and that's the reason why these clouds are really highlighted here. And the natural color RGB only uses visible channels and the near infrared channels, and so these clouds, these thin clouds, are optically too thin for them. So always keep that in mind if you use the natural color RGB for presentations or for making your forecasts, that there's some things missing. Okay, but now let's jump back to the end of summer. So I would like to start with Saturday, the last summer day we had over here in Austria. And you can see here the RGB and the absolute topography in 500 hectopascal. You can see here this gentle westerly flow, some more or less pronounced ridges and trough. And this frontal system with a cold front over here, some embedded convective cells can be seen, and this warm front feature that caused these thin cirrus cloud fields. And what happens next, as you may imagine, is that this frontal system is moving eastwards. And this is now Sunday. The frontal system has appeared in Austria. It didn't bring the thunderstorms we thought it would bring because this cold front came step by step. So the first session, the first showers were already there in the morning and brought also some wind shift from southerly to west directions, and so most of the Cape was already used in the morning. But what is more important in this image is probably the feature here over the Atlantic, this really distinct glow over there. And as you can see, with the help of the color, these red colors, this always indicates that further development is going on. And as we can see in the next image, so concentrate in this area and on this frontal system, you can see we have a really, really pronounced glow now over here only. So the last image was only 24 hours before, so this has really developed into something really big, and also this frontal system got really pronounced, but also this ridge, which is now stabilized by these two upper level lows, is really more pronounced now. So it's Monday, start of the new week, the day before yesterday, and you can see here over Central Europe this upper level low and this frontal system. And on Monday we already had really autumn weather conditions with highest temperatures below 20 degrees, some heavy rain showers. And as you can see, 12 hours later, a really, really blocking weather situation has formed. So in the German-speaking area, we call this kind of pattern an omega weather pattern because it looks like the Greek letter omega. So the low on this side, then the ridge, and the low on that side. It looks like an omega if you draw it. And this is a really blocking weather pattern because the low stabilizes the high, and the high stabilizes with the low. So this really won't change for some days. And another area of interest is now this area over here in the northern parts. You can see this, this cloud system, and there's a shallow trough over here, but as the color indicates, you again see this really reddish colors, which are a sign for PV advection, which always shows that further development is going on. And if we now take a look at yesterday, 18 UTC, you see that only 6 hours later, this distinct glow has formed, and the frontal system is even more pronounced. And as today, the weather situation looks like this. So again, the omega pattern is really stable. So if you are situated somewhere in the area of this high pressure system, you might be lucky because I took a look in the forecasting charts, and this weather situation, it will dominate the weather throughout Europe until the beginning of next week, so until, let's say, the beginning of September. And if you're somewhere on the main parts of Europe, then you will have more or less unsettled weather conditions with this trough and this upper level low there going on, and it's colder than it should be at this time around. And so, as you may probably know, we have on the on the EUMeTrain website these sat cams going, and I thought it would be a nice idea to see what the weather looks like, for example, in the sphere of influence of this upper level low and in the sphere of influence of this upper level high, or this high pressure system. So at first I would like to take a look at Helsinki, which is situated somewhere here, let's say. So, oh no, sorry, there's again another chart, I forgot about that. Yeah, here we can see all the frontal systems. You see this very distinct frontal system over here, and in blue you can see the thermal front parameter, in green you see the thickness pattern, which is a sign for the temperature. And you can see this frontal system here is very pronounced, as the temperature gradient is really sharp. But thanks to the high pressure system over the United Kingdom, this frontal system is really, can't really move forward. And also this frontal system over here, also the temperature gradient is really sharp. This will bring further cold air outbreaks to great parts of Europe. So, but now let's take a look at Helsinki. Yeah, as you would expect, the sky is mainly overcast. You can see the streets are wet. I think this person here is even using an umbrella. So yeah, if you're on this side of the blocking weather system, then you don't have the best weather outlook for the next few days. But if you are, on the other hand, somewhere situated on the United Kingdom, looks like this. We have here the Scottish Highlands, and yeah, blue skies as far as you can see. And let's take a look at Salzburg. As I have told you, the subtitle of this weather briefing is the end of summer or the beginning of autumn. And in Salzburg, the current weather situation looks like this. So the sky is partly sunny, partly overcast. I'm sitting somewhere down here, so this is a webcam taken from the local city mountain, the so-called Untersberg, and you can see not the best weather conditions today, but at least it's dry over here. And as I've said, the weather prevails mainly unstable over continental Europe for the next week. And if you're somewhere in vicinity to this high pressure system, you're really lucky, because we really have some nice summer days to be expected. So that's it from my side. If you have questions, you can always ask them after Andreas' presentation. And so I would now like to give the word to Andreas.
Yes, thank you, Lily. I'm going to share my presentation, and I hope you can see it all. So welcome also from my side. My name is Andreas Wirth. I'm working at ZAMG, like Lily, but not in Salzburg. I'm in the headquarters in Vienna. So, and for the rest of the weather briefing, I would like to talk a little bit about upper level lows. I called this presentation a few thoughts about upper level lows and why. There was a very pronounced weather situation in mid-July, which was in the beginning of the summer, which brought a lot of rain and inundations and floods to Central Europe. And these were caused mainly by an upper level low that was stationary for a long time over Central Europe. And yes, let's have a look what upper level lows are. So the upper level lows, once they are formed,
Sorry,
yes?
sorry. Are you going to?
Oh, sorry.
Mode? Yeah.
Yeah, you're right. I want to go to the presentation mode. I forgot it.
Yeah, no problem.
Yeah, the upper level lows are tightly connected to the Rossby waves, and they can be seen here. The waves over the northern hemisphere and the pink line is more or less the polar front. If the Rossby waves have a small amplitude, it's called a high index circulation. If they have a large amplitude, it's called low index circulation. So, and now to you, question, on average, where do you think on the higher index circulation or on the low index circulation, where do you think we have the stronger north to south temperature contrasts? Either with the high index circulation or with the low index circulation. So where are the north to south temperature contrasts stronger? You can annotate it, just make a cross or on the...
You have to start annotating.
I have to start it, okay. So, and okay, so now you should be able to annotate. So where are the temperature contrasts? It's an easy question. By the way, the omega situation Lily showed before is a low index circulation, yes. So, okay, yeah, the high index circulation is the favored answer. Locally, you can have very strong temperature contrast, even in a low index circulation. But on a global scale, on average, the temperature contrast is higher in the high index circulation, which makes that the jet streak has a rather linear path around the globe. While when the temperature contrast is not so strong, then we will have this meandering jet stream. And by the way, if the climate models are right and the poles are getting warmer and warmer, the temperature contrast will probably decrease and we will get more and more low index circulation situations. And this will have also an impact on weather, because this is the way upper level lows are formed. They are not so much or not at all formed in the high index circulation. We need a low index circulation for upper level lows to form. So let's continue. So the upper level lows are coming from two possible origins. Either it's an old frontal system which fills up near the ground and still the low and the high levels remain. This is sometimes the case, but not so often. In the most situations, you will have, like you see it here, a very pronounced trough, and you will have in the trough, inside the trough, small lows in the higher level. This is the geopotential height at 500 hectopascal. You will have two, maybe sometimes three upper level lows in this trough, depending on its size and its length. In fact, this is an upper level low, but this is not a typical or not the real upper level low that we are talking about. We need a process that is called cutoff, tear off, cutoff, and then we have the upper level low. And this is shown in this graphic. I will stop it. So this is the beginning. We have the frontal zone, which has maybe, for example, the polar front. And we have a wave, and this wave continues to grow. The amplitude of the Rossby wave is increasing, and continues increasing until we have this it's called tear-off stage. Here we have a bottleneck, and the low drifting to the south. And finally, this is the last stage. I wanted to go back. This is the last stage when we have the upper level low separated from the main frontal zone, from the polar front, and being situated in the warm air south of the polar front. So this is a cold air drop, see, cold, in the warm air. The blue is, again, as I told you, the geopotential height at 500 hectopascal, and the green lines is the temperature. So let's continue. This is a real-life example of such a cutoff process. You see that the trough develops, gets deeper, and now we have the tear-off process where the warm air on both sides of the drop joins and the upper level low moves to the south and then is separated from the polar front. What is interesting here is that the gradients here in the trough are very strong, and later on, let's continue the loop, you will see from a certain point on the gradient in the south. Just a moment. Yeah. I cannot show you the mouse. It does not work at the moment. Anyway, the south of the cold air drop, you see that the gradient is not that strong anymore as it was before in the trough. And if we continue the loop, you will see that once the upper level low is finished or existing, so I stop it here, the gradient around the cold air drop is quite uniform. Not like in the trough with a very steep gradient in the southern part, it becomes more and more regular. So this has an effect on the jet. So this is a typical upper level low. This is, by the way, the one that brought that precipitation over Central Europe in July. And you see the jets here, the jet streaks in yellow, over 30 meters per second. That they're around this upper level low, around this cold air drop, because the gradient, the pressure gradient, is very similar all around it. This is not the case on the right-hand image with the trough. On the trough, you have the jets most of the time, not always, but most of the time on both sides of the trough, here on the back side and on the front side. And now I ask you for this image, for the trough image, to show me where the gradient, the pressure gradient, is strongest in the trough. And I have to allow you to annotate. Okay, and I think I have to tick again. Okay, I see. So the question is, where is the pressure gradient strongest in this trough region? And maybe same similar question, where is the curvature? Where is the curvature the strongest? Where is the jet or the air has the strongest curvature? Okay, yes, exactly. This is what I wanted to see. Thank you. So I stop annotation. Jochen Kerkmann, in one of his presentations, had a similar situation, and his question to the audience was, and I will give you the same question, why don't jets like strong curvature? So you see here, this curvature is not too strong, but as the curvature increases here, and it's strongest here in the southern part where you have marked it, the jet disappears, the jet streak disappears. The jet is still there, but that jet streak disappears. And then it comes again here. And Jochen did not give an answer, and I will also not give you an answer. I will leave it up to you to think about it. Why don't jets like strong curvature? This is something maybe you have to think about it. If you know an answer, already know, you can put it in the chat, but I will not give it now. Well, I told you already, upper level lows are in connection with heavy precipitation, and this is what happens. It's a photo from the fridge of my parents. They left this summer and left the freezing part of the fridge a little bit open, and that after 2 weeks or 3 weeks, I don't know, they came back and opened it, and that's what they saw. So it was a mess, and it's the same thing with the upper level lows. You have a cold air drop, the fridge, in a warm environment, and you have a lot of condensation and processes that go on. So it's very important regarding the surface weather, a lot of rain, because it's a cold air drop surrounded by warmer air masses. And this was the same here with the fridge of my parents. This special situation that was causing the floods in Germany and also in Belgium had also an impact on Austria, not that bad, lucky for us, and there were no fatalities, but there were strong amounts or heavy, big amounts of rain. And this is a photo from Liliane. It's a small town south of Salzburg, along the Alps, and you see that the rain comes down the hills, and there where you usually have streets, you find a river. This is our prognostic tool, or for Inca, for the very near time, and it's also showing the accumulated precipitation for the last 24 hours. And what you see here, the upper level low, at this time is already over the Mediterranean Sea, brings a lot of moist air around the Alps, so they contour the Alps, and you see the effect of the Alps because the precipitation, there is a barrage, and the precipitation is falling along the edge of the mountains. You have yellow precipitation regions, that means more than 130. One day later, the amount of precipitation is a little bit shifted to the east because the upper level low moves also slowly, but it moves. What you see also is here an image from 17th July when the upper level low is already over the Adriatic, and you see in this image a lot of convection. So you have a lot of precipitation anyway, but locally it's even increased due to convection. So it can be very, very unhomogeneous. And you see the warning was quite okay. It's along the Alps, and the flashes means thunderstorms at this stage. And you have some measurement stations that show 100 millimeters in 36 hours upwards to 170 millimeters. And all these towns and stations are located north of the Alps. So the humidity is brought around the Alps, and it's falling on the northern part. So this was my last slide, and a few thoughts about upper level lows. To finish, and I hope I'm in time, yes I am, I would like to advertise the next weather briefing. It will be held by IPMA, by the Portuguese Met Institute, on 20 September, same time. So I hope to see you there. And now I would like to see if there are some answers. Overall, jets experience instabilities while curving. Hence, the jets must slow down in curved environment. Yes, exactly. It must, exceptions of course. Yeah. I do not want to give you the answer. I think maybe something similar than to me happens to you. When I got the question, I had to think for a longer time, but in the end, it's not so difficult. You have some answers already here. So, why don't jets like strong curvature? This is the question of the day.